And hello again. It's been about a month since the last update, so I thought I'd give a little bit of progress. And as you can see, I've kind of glued everything, sometimes literally glued everything to the outside of the case, kind of making more of a compact thing here. And it began looking kind of like a movie prop explosive device, which is kind of apt because I'd like to spend a little time talking about safety. There was an incident. So after gluing all this stuff together, I realized that I couldn't really plug this into the power strip anymore. So I thought, okay, not a problem. I'll get myself an extension cord, and I can just plug the extension cord right into here, and no, not a problem, right? So I went down to the garage, got myself an extension cord. Now you can probably see something is wrong here. I didn't think anything of it at the time, and what you think is wrong is not actually a problem. The missing ground pin on this plug here doesn't actually matter too much because the ground pin on the device isn't connected internally. It just goes straight through to the ground pin on the front, just a pass through. So I thought absolutely nothing of it because I knew that the ground didn't actually make a difference. What does make a difference, however, is the polarity of the plug. And without the ground pin, it's all too easy to plug this rather old extension cord in backwards. Now, normally, again, that would not be a problem because you have live and neutral here in the United States, live and neutral. And since it's AC, the voltage is flitting back and forth anyway, so normally it doesn't make too much of a difference, especially with motors and stuff like that. But in electronics like this, there is a rectifier in here and a capacitive dropper power supply. I haven't really reverse engineered the circuitry in this thing yet. And I might do it just to see exactly what happens, but long story short, the neutral, which I've written here on the back here just as a solemn reminder of exactly what went wrong, the neutral is internally referenced to the ground potential of the internal digital circuitry. So what normally would be the ground or the battery minus, if you will, for the electronics inside is referenced to the neutral. And it's got I measured a couple times. It's got anywhere from 2 to 20 ohms of resistance. I don't know why it changes, but we'll just hook this back up. We'll go to here. And you'll notice I go right to the shielding on the USB because that's relevant to what happened. So we got about 5 ohms. Okay. So if you plug this in backwards, and normally like a newer extension cord or something like that would have one pin bigger than the other, like you can see on the front here. One slot is bigger than the other. The bigger slot's neutral and the smaller slot is live. That means you can't plug in, if the plug is up to spec anyway, you can't plug in a non-grounded plug backwards because the blades are two different sizes. But it's okay, like on this device here, you can see the two blades are the same size. That's fine because you got the ground pin, which acts as a polarizing element as well. So you can't plug this back in backwards either. This you can. So when I accidentally plug this in upside down, boink, live was neutral and neutral was live. Okay, now this is not necessarily a problem because everything in here is kind of self-contained and it's got the rectifier in it, which keeps the voltage in the right polarity for the electronics, except that now what would be the ground plane inside is now at a rectified 120 volts AC, which would be about 170 volts DC. Okay, and as you can see, I have the ground plane of the electronics inside hooked up to the Arduino. Again, still not a problem. It's just that this metal here, and just about any exposed metal, especially like on the back here, any ground here would all be at 170 volts DC with respect to earth ground. That could be pretty dangerous, although I managed to not shock myself somehow. I guess I just got really lucky. The problem is when I went to plug this into my computer. Because the ground on the USB port on the front of my computer is connected straight to earth ground through the power supply. And through the motherboard, really. So everything is connected to earth ground there. This earth ground, or the shielding and the ground pin inside the USB port, were both at about 170 volts DC. And the USB port on my computer was at ground's potential. Plug it in, there was a little flash and a pop and a puff of smoke, and I blew the ass out of the Arduino, and also completely nuked the USB ports on the front of my computer. Fortunately, nothing else was damaged. The kilowatt unit itself is fine. Actually, I say that I blew out all 5 of my comparator chips, so I replaced those. Luckily, I had enough spares, just sitting in a drawer. But yeah, so that was an interesting experience, and not a terribly expensive one. I got a new Arduino, of course. That was like $12 or whatever, and I have plenty of unused USB headers on my motherboard, so I just moved the wire over to the next one, and everything's hunky dory. Yeah, lesson learned. So we are not going to be doing this crap anymore. Instead, where did I put it? Ouch. I just stabbed myself. I made this little whip. So I can plug this in here like this. And then I can plug that into my light bar. And everything has a ground plug. Again, you can see these pins are the same width, but because of the ground plug, it'll only plug in one way. We can turn that on. And you can see the unit is now on. But I know that this here is at least neutral potential. So I've already checked the voltages, so I'm comfortable touching that. Because I've already gone through with my multimeter and checked all the voltages and everything. It's the wiring in my house is good. Otherwise, if there was a problem with the wiring in the house and the neutral is not necessarily at ground potential, even though it should be, they're supposed to be tied together in the electric panel. But yeah, it's only a couple of volts difference between here and ground. But if you ground this out, it's no big deal because the wiring is fine. But even so, I went ahead and when I bought the new Arduino, I went ahead and got a little USB isolator. This is advertised as 4K, but I don't know if you can see the trace in there. That's about maybe at best 2 millimeters separation. I don't know much about isolation, but I'm willing to bet that 2 millimeters is not 4,000 volts worth of separation. Doesn't matter. This thing actually seems to work. And got it all hooked up again. It runs fine. You can see I added a few extra things. I added a switch. This is a toggle switch. So I can actually not have to deal with the wiring and everything. Let's go over the features. Let's unplug this because it's actually kind of unwieldy. Drop that on the floor. So I had 9-volt batteries before. This battery is almost dead. It's outputting about maybe 7.5 volts, but that's fine because it's regulated down to 5 volts inside. As long as I'm above 5 volts, the regulator can do its job. It's just a linear regulator anyway, so I'm not too worried about it. All the wiring comes across here into the Arduino. And what I'm doing here is I have the 4, we'll call them rows, the 4 row drivers go into these pins here, and I can put software interrupts on these, or external interrupts rather. So I'm triggering interrupts on these 4, and then I'm inputting the other 16 column drivers, or column line signals, whatever you want to call them, the columns, as 2 8-bit bytes using this port here. So basically I wait for this to trigger, and then I input these, and then I wait for the next one to trigger, and input again, wait for the next one, and again and again. And I collect all that information, and then it's really just, it's not really a lookup table, but I analyze the pattern of the bits, and I can figure out what the display is saying. And there's a little bit of a bug in there, because some of the digits don't work right, but overall it works okay. So what I've done here, and this is something new too, this whole board here with the comparators, I take the signal out, I put it through a comparator, and I use a voltage reference, and this conditions the signal, and it gets rid of a lot of the noise, and it gives me a nice, clean signal to work off of for the Arduino. And that works pretty good. In fact, let me draw up a little diagram for you. So this is what the comparators are actually doing. The signal, which this will be the rows and this will be the columns. So the row goes low first, then high, and the columns go high first, then low. Not a big deal. But we feed these into the comparators. I have voltage references for the rows. Just tweaked it until it worked good. So we have 3.63 volts here and 0.48 volts for the rows, for the columns rather. So basically, as soon as the voltage on, let's say, the row signal goes above this threshold, is 3.63, the output of the comparator is shorted to ground. So with the help of a pull-up resistor, or is that backwards? No, this is right. With the help of a pull-up resistor, this is the signal that we get. It's normally shorted to ground, and then it pops up like that. Fortunately, the microcontroller has an internal pull-up resistor, so all we have to do is configure that, and we don't need any extra components, because the comparators take care of everything outside of that. I don't know if you can make, even I can't make that out. I'd have to sit there and study. It's been a couple weeks since I made that, so I kind of forgot how it went together. But this is right. This gives you an idea. And what happens is now, because I have two different voltages, I tried using the same voltage reference, and that causes this peak to be offset. Or rather, I had it going where the row would trigger first, and then the column would trigger. But there's like a couple of microseconds difference between the falling edge of this and the rising edge of this, and I couldn't reliably get the microcontroller to skip past that. The microcontroller is actually very quick, and was able to pick up the, I think it was like 4 or 5 microseconds, something like that. It varied too, which is a real pain in the butt. But by using two different voltage references, I'm able to trigger the signals basically at the same time, because they're at different levels at that time. So now I can trigger on the rising edge of this, and then I can read this. I have, I forget what the time was on this. It's several milliseconds. It's like maybe 2 milliseconds, I want to say, which is an eternity for the microcontroller, because that's running at 20 megahertz, so not a problem. Trigger that, collect the data, then wait for the next trigger on the next row driver, and we're done. Boom. All right, and here you can see the actual information coming through. You can see that the data coming in doesn't quite match that for whatever reasons. Let me change something here. You see that goes to 0, like it should. Okay, it's still 0. And this is what I was talking about before. There's something not quite reading correctly with that. I wish there was an easy way for me to change the voltage, but there isn't. Let me try turning the power off. And of course that would stop because I'm an idiot. Okay, so let's turn the battery power on. We'll use the switch. And now I can turn off the AC power without losing the controller. And you can see the voltage drops like that. And you can see that it's accurate to a point. Right? But like I said, under certain values that are displayed, it's not reading right. I think that's just a software bug, because obviously everything else works right, so whatever. And this is the logic analyzer data that I get out of the pins. This is downstream of the comparator. We just kind of look here. The first 4, of course, are there's a one-for-one correspondence between the channel and the pin as it comes out of the device. So you can see the first 4 channels are again, we're calling these the rows, right? So row 4 goes first, and then row 3, 2, and 1. And you can see these spikes here. These are long enough to trigger the microcontroller, but not long enough to actually matter. So it's important that this is what the debugging is supposed to take care of, right? In fact, this might be part of the problem, although that's, yeah, maybe I need to do something about that, because we're at, well, no, because I'm waiting 500 microseconds, right? And this is only about 18, 19 microseconds. So, okay, so 500 microseconds is actually quite a long time. That's more than I can show here. Hold on. Whoops. That's about 500 microseconds right there. So I can slide this window around. So that's how long I'm waiting. Come on. I don't know how I got scrolled down there. All right. So let's go over to, say, the beginning of one of these triggers here. It's a little awkward to use this software, but so I would be triggering off of that, and then I would be waiting 500 microseconds. So I'd be waiting well into that pulse, as you can see there, and then taking my data sample. But you can see the little spikes here and all over the place. by waiting, I basically skip over that, and I don't think I've ever seen a spike that is more than 500 microseconds. But these are all the different channels here, and you can actually go through with a little chart I made and pick out, okay, if this row here and then these bits here, and that's what's being displayed. And it's really kind of neat to really kind of see this information and get it, it becomes real at this point, I feel. So this is very useful, and my analog oscilloscope can't handle this. And even if I had a digital scope, a halfway decent one would be like 4 channels. That wouldn't be enough to really do what this logic analyzer can do. So worth every penny.